One of the most potentially dangerous volcanoes in all of Africa is located within 10 miles or 16.1 kilometers of approximately 1 million people. I am not referring to the Democratic Republic of the Congo's Nyiragongo volcano, but rather a complex which has proven to be far more explosive. What I am referring to is an explosive alkaline shield volcano known as Menengai, which is located just north of Kenya's third largest city by population, Nakuru. Here, there is a vast 11 by 9 kilometer wide depression in the ground which is up to 500 meters or 1,640 feet deep. This caldera formed in one of the continent's largest geologically recent explosive eruptions approximately 12,345 years ago, meaning almost every lava flow contained on its surface within has erupted since. Thus, depending on the source in question, Menengai may have erupted as many as 60 times in the Holocene, with some of its youngest lava flows containing exposed fresh-looking black rock, possibly being under 500 years old. While such a vast volcano does create a potential for future hazards, we actually don't know much about it since it is honestly understudied. We don't know the age of its post-caldera eruptions, and sources actually disagree on the age of its latest caldera-forming eruption. However, in historical times, this volcano has shown no signs of unrest, and in fact, its existence proves as a crucial part of Kenya's economy, as a series of geothermal power plants are being constructed due to its vast underground geothermal potential energy having the theoretical potential to produce up to half of the nation's electricity. But why does this volcano exist in the first place? What future hazards might it pose? And why is it considered to be a shield volcano despite the highly viscous coulee-forming lava flows it erupts? For reference, the Menengai Shield volcano is located in southwestern Kenya, 150 kilometers north-northwest of the nation's capital city of Nairobi. Like most volcanoes in the country, Menengai exists due to the slow rifting apart of the Nubian Plate to the west and the Somali Plate to the east. This rifting motion averages 6 millimeters a year, which over time has formed vast rift valleys that have provided a path of least resistance for molten rock to intrude into. And, due to these exact specifications, resulting volcanoes that do form are often alkali-rich, which, in the case of Menengai, is primarily involving the rock type known as trachyte. Trachyte is a highly viscous type of lava which is too slow to form runny basalt-like lava flows, instead building up into both lava domes and thick, slow-moving lava flows often more than 100 feet in height known as coulees. These coulees began erupting from the edifice of Menengai 200,000 years ago, with intermittent eruptions occurring from separate vents. Because of the area's fairly flat topography, these lava flows rarely float on top of one another. As a result, over more than 100,000 years, a fairly gentle sloping 13-kilometer or 8.1-mile wide shield volcano was constructed. Two groups of flank vents also formed during this time span, specifically a series of explosion craters to its south and a series of vents on a volcanic ridge to the north-northwest. Then, due to the buildup of pressure from the presumably abundant volatiles in its large underlying magma chamber, eventually a major ultraplanian eruption was triggered 35,620 years ago. This eruption generated a towering eruption plume and caused dozens of meters thick of ash and tephra to fall across a sizable area. As pyroclastic flows raced across the landscape, incinerating essentially everything in a 20-kilometer radius, the volcano's magma chamber was largely drained. Then, due to the large amount of erupted material, totaling 26.1 cubic kilometers of material, the ground overlying the now partially empty magma chamber collapsed downwards, forming a large caldera. However, the caldera formed by this eruption was smaller than Menengai's modern caldera. That modern caldera would form in a similar eruption 12,345 years ago, depositing a layer of tephra up to 80 meters or 262 feet thick and ejecting 25 cubic kilometers of material. An estimated 25 cubic kilometers of lava has erupted since then via numerous trachyte coulees, but the number and exact ages of these flows is still not fully studied. Any future eruption from Menengai would, in my opinion, likely have some form of explosive component to it due to the viscosity of the lava involved, with a Merapi-type Vulcanian eruption seemingly most likely. This means future hazards were a moderate-sized eruption to occur again one day would mostly include advancing lava flows, volcanic gas, medium-distance pyroclastic flows, and ashfall. If this overview of the Menengai volcano sounds bare bones, that is because it is. Simply put, Menengai needs to be better studied, especially to determine its recent eruptive history. As a final note, I would like to thank my new YouTube channel member, Mark S., for supporting my work.